And we know that if something is a function, x never repeats. If we're looking at the graph, it passes the vertical line test. In this section, we are going to be talking about one-to-one functions a lot. One-to-one function means two different inputs correspond to two different outputs. In other words, if you have different x values, you have to get different y values. Another way of saying that is y never repeats. Okay, so in a function, x doesn't repeat. In a one-to-one function, y doesn't repeat either. So, let's look at some examples. Let's decide if each of these is one-to-one. So what would the first one be? No? Why? Okay. Is B one-to-one? Yes, because if you look at all those y values, they're all different, so it is. A lot of times instead of writing out one-to-one, I put 1-1, just a shorthand. The algebraic way of doing this, if I ask you to algebraically show me that two functions are, or that a function is one-to-one, what we have to do is take two different x values, plug them in, and set the y's equal. Okay? Then, if I do that, so I plug in an a and a b, and I solve this and get a equals b. That means if the y's were equal, the only way that happened was if the x's were equal. That tells me they're one-to-one. If I solve this and I get something other than a equals b, like a equals plus or minus b, that could mean that the y's were equal if the x's were the same or if they were different. And so then in that case, it would not be one-to-one. So I want to look at an example and see if we can make a little sense of what this is telling me. I want to decide if these are one-to-one. So one-to-one says y never repeats. So we start out pretending y does repeat. So y, that's your f of x. Let's say f of a equals f of b. These are two y values. I'm going to say those y values are equal. So I hit the same y value twice. F of a is negative 3a plus 7. F of b would be negative 3b plus 7. We're just going to solve for a. So if I want to get a by itself, we can subtract our 7, divide by negative 3, and we get a equals b. So I started this problem by saying, okay, I have two y got repeated. I have that same y value twice. And I found out that the only way my y would repeat is if those were the same x to begin with. So this means they are one-to-one. At B. I want to decide if this is one-to-one. We set two y values equal. F of a equals f of b. F of a means you plug an a into your problem, so you get 49 minus a squared. F of b means you plug in a b. If I asked you to solve this for a, what would you do? Get rid of the square root. We could square each side. If I subtract my 49, divide by negative 1. How would you get a by itself now? Square root. If you add a square root, what do you have to put with it? So the A equals plus or minus B. Wouldn't what?
Like with the first square root of A squared would just be A.
No, because there's two terms. The 49 minus the A squared, since it's two things under the radical, you can't cancel. Now, if it were like 49 times A squared, just a single term, then you could turn that into a 7A. So what I found is that my Y values could be equal if I put in the same X, or if I put in a positive and a negative. So for instance, if I put in positive 7, I get out 0. If I put in negative 7, I get out 0. So two different X values could give me the same Y. So is this 1 to 1? No. So this one is not 1 to 1. Typically things that are going to make it not 1 to 1 would be like those even powers, squares, 4th power, 6th power, anything where you would have to add a radical and that would make it plus or minus in there. Absolute values would not be 1 to 1, so those are kind of the big ones that we will look at. Are there questions on this? So the algebraic method, we can do it, but it's usually not anybody's favorite. We can also tell if things are 1 to 1 by looking at the graph. If it's a function, x doesn't repeat, so that means the graph passes the vertical line test. If it's 1 to 1, y can't repeat, so it has to pass the horizontal line test. So if every horizontal line only hits the graph in at most one spot, it's 1 to 1. So in other words, if you can draw a horizontal line that hits that graph more than once, it is automatically not 1 to 1. So let's use that. Take a second, sketch these graphs and decide if they're 1 to 1. On a line test. So this is not 1 to 1. You can draw lots of horizontal lines and hit it more than once. X cubed is the chair. Is that 1 to 1? Yes. So that one is 1 to 1. All right. Any questions on that part? If a function is strictly increasing or decreasing, so that means like it always increases or always decreases, that means it's automatically going to be 1 to 1. Which if we think about, if you have a function and it just keeps going up, it'll never hit the same y value twice. You only have that issue of failing the horizontal line test if you switch direction somewhere along the line. If you were going down and you start going up, or vice versa. The whole reason that 1 to 1 is important is because if a function is 1 to 1, we can find an inverse.
So, isn't that only if I mention an exponent?
Yes. Or an absolute value. Or a plus or minus.
Okay, so now.
But for the most part. I mean, most of the problems we will encounter, yes. In the whole scheme of things, not really. Okay. So, we can find inverses if it's 1 to 1. And when we do that, we just reverse the x and y values. The reason it has to be 1 to 1 is if you try to find the inverse of something that wasn't 1 to 1. So just a very simple example, let's think about x squared. If you reverse your x and y's, it would look like this when you did the inverse. What do you know about this? This doesn't pass the vertical line test, does it? So if the original isn't 1 to 1, then the inverse isn't a function. That's why we really focus on only the 1 to 1 pieces, so that when we find the inverse, we still have a function to work with. So let's do just a basic example to start. If I just gave you a set of ordered pairs, I asked you to find the inverse, what would you have to do? Flip the x and y's. So if -3, -27 was in there, then the inverse would have -27, -3. You don't change the sign, you just change the order. So we'd have -8, -2. -1, -1. 0, 0. 1, 1. 8, 2, and 27. You guys go ahead and do B. Find its inverse for me. So what's the inverse of this one? Okay. So easy enough? Good with that stuff? So what we see is that the original, those x values become the y and the inverse. What that means is the domain of the original function is equal to the range in the inverse, and vice versa. The range of the original is the domain of your inverse. Your domain and range are just going to flip roles as well. So this next slide, we'll go ahead and talk about it. Debating. A function, the inverse of a function is like the opposite of it. So if I said my operation is x plus 7, what would the inverse be? Well, if we're just doing the very basic, like the opposite of adding 7 would be, so x minus 7 would be the inverse. Now, if I pick a number, give me a number, 8. 8 plus 7 is 15. 15 minus 7 is 8. Okay, well, if I started the other way, if I started with 8 minus 7 is 1. 1 plus 7 is 8. So if you do both a function and its inverse, if you do both operations, they will cancel each other out and you should get x back for your final answer. So sometimes I might give you two functions and ask you if they're inverses of one another. And the quick way to do that is to compose them. F composed with G and G composed with F. If they are inverses, both of those answers should give you x back. In general, you do need to check both. They both have to give you x, not just one of them. But if one doesn't, then there's no need to check the other one. We already know they're not inverses. So I've got several examples on here of this. We'll do a few of them. I just want to know if these are inverses or not. So this is only one way of figuring it out, but we could do the composition. If they're inverses, they should cancel each other. So we can do F composed with G and G composed with F. And what answer do I want to get back both times? X. If they're inverses, they're going to cancel each other. So F composed with G means F of x cubed. So if we go to F, that is the cube root, and we are replacing our x with the x cubed. What happens? They cancel and you just get x. So that one worked. It's not enough. We need to check the other direction as well. So G composed with F means G of the cube root of x. So go to G. So it would be the cube root of x cubed, which is So that one worked as well. So these are inverses of one another. They are the opposites. How much of this stuff do you guys remember seeing in Algebra 2? We did. I promise. So I want to see if these are inverses. So we can compose them. F of g of x. Start on the inside. G is 1 over x minus 1. Plug that into f. So 1 over x minus 1 with a minus 1 on it. If I combine like terms, we don't leave fractions within fractions, do we? What's a quick way of getting rid of that? We could times x on top and bottom. So that gives me x over 1 over x times x is 1 minus 2 times x. Regardless of how far we simplified this, what did I not get for my answer? X. So what does that tell me right here? Not inverses. Is there any reason for me to check the other one? No, we've already established these are not inverses. Why don't you guys do the next one? F of g of x would be f of 1/3 times x minus 4. Put that in. Three times 1/3, what do those do? So you have x minus 4 plus 4, which is other direction. Plug in 3x plus 4. So you have 1/3 times 3x plus 4 minus 4. So the 4's drop, so 1/3 times 3x is x. So yes, these are inverses. Any questions there? We're going to talk a little bit about the graphs of functions and inverses, and then we are going to actually just practice finding inverses, and that will be our end for today. So, we know that if you have a function, you just reverse the x and y to find its inverse. What that means is that a function and its inverse are always going to be symmetric across the line y equals x. I'm just going to do one and draw in that line to kind of illustrate that, but because all you're doing is literally reversing the x and y, you're letting your x equal your y, that kind of becomes a line of symmetry in these. So let's say I asked you to graph the inverse of the line y equals 3x minus 2. We know how to graph a line, don't we? So let's graph this to begin with. This is a y-intercept of -2, slope 3, so about 3 over 1. And there's our graph. Okay, so if I wanted the inverse, we just need 2 points to draw a line. We have this point, or this graph has the point 1, 1, so if you reverse x and y, it's still 1, 1. Then I had 0, -2, so that would become to 0. So I have those 2 points for my inverse. So that would be the inverse right there. So I just took the 2 points that I graphed on my original line and reversed the x and y. The line of symmetry, I told you it would be y equals x. If you graph that line, it's a line y-intercept of 0, slope 1. So it looks something like that. Assuming my original lines were straight and my scale was perfect, do you see how that red line would go right through the middle of those graphs? In Algebra 2, when we found inverses and graphed them, a lot of times we would graph this line just as a quick check to make sure that our inverse looked correct. That would help us find some of our mistakes there. Questions on that? So the next one, I just gave you a graph. I didn't give you the equation. And I'm asking you to find the inverse of it. So to do that, we really just need to find some points on this graph. For instance, I have the point 1, 2, so that would go to 2, 1. I have the point 0, 1, so that would go to 1, 0. I have negative 1, 0, so 0, negative 1. So that's that first little section. Negative 1.5, negative 1 would go to negative 1, negative 1.5. I have negative 2, negative 2, so that stays. My graph is not perfectly square, so that is slightly off there. But it should look something like that. So if I give you a graph itself, you can just take points on that graph and reverse the x and y. Any questions there? All right, so the last topic that we need to cover here is actually finding an inverse. And this is what, in Algebra 2, we did the most of this. If it's written as f of x equals, we first change that to a y. Then we flipped x and y, solved for y, and at the very end, we went back to the function notation and replaced that y with an f inverse of x. So let's practice one. We'll start off with a nice one. Okay, so step 1, f of x becomes y. Step 2, interchange x and y, so it becomes x equals 2y plus 3. Remember, if you have multiple x's over here, every x becomes a y. Okay, now we just solved this equation for y. So we could subtract our 3, divide by 2, and instead of y, we write f inverse of x equals x minus 3 over 2. I'm going to do another one with you, and then I'm going to do this one. No, you could write 1/2 x minus 3/2, or 1/2 parenthesis x minus 3. Any of those would be fine. Anything else? Let's do this one. So step 1 becomes y equals step 2. So it becomes x equals, I have 2 x's in the original, so those both become y's. Okay, I am trying to solve for y. What do you recommend?
Get the y out.
Okay, we need to get rid of this fraction, don't we? We can't just cancel these y's because I have more than one term, so really the only option to get rid of this fraction is to multiply by y minus 1. Those cancel. If I distribute, I get xy minus x equals 2y plus 1. I am trying to solve for y. I have 2 y's, so what we need to do is put everything with a y on one side of the equation and everything without a y on the other side. So we can subtract over this 2y and add over this x. Can you actually add xy plus or minus 2y? No, so I'm just going to leave that. Over here I have a 1 plus x. Close. I could divide by x, but that wouldn't help with this term. So instead, if I were asking you to find like when 3x squared plus 4x equals 0, what would you do? You would factor, pull out an x. So right here, we can pull out a y. Now you have y times something, so we divide it. Am I done? Mm-hmm. Now, final thing I need you to do, instead of y, we write f inverse of x equals 1 plus x over x minus 2. So that one was definitely a little more involved. I did ask for something else on this problem as well. I wanted the domain of range. I want domain and range of the function and the inverse. So I use D for domain and a subscript to tell me like domain of the function, range of the function, domain of the inverse, range of the inverse. I have to find all 4 of those. Domains are easy. We know if it's a fraction, the bottom can't be 0, and if it's an even radical, whatever's underneath has to be positive. If I'm talking about the original function, what can x not be? 1. So the domain of the original function is negative infinity to 1, union 1 to infinity. We haven't talked as much about range, but we actually don't need to know anything about the range right here, because the domain and the function, those are the x values in the original, those become the y values or the range of your inverse. So I know these two things have to be equal. So the range of the inverse is negative infinity to 1, union 1 to infinity. I also know the range of the function will equal the domain in the inverse. So we could just look. In our inverse right here, what can x not be? So the domain of the inverse is negative infinity to 2, union 2 to infinity, and that becomes the range in the original function. So really, all you have to do is look at domains, and you get your ranges for free. Questions on that? I want you to try the next example on your own, and then the final example I think I'm going to make a switch to, and we'll look at that one together. So try this one. You don't have to do domain and range on this one, just find the inverse. Change f of x to y, switch x and y, solve for y. So add 1, and divide by 2. How do you get rid of a third power? Cube root. Do you need a plus and minus with that? No, if it's an even root, you add the plus and minus. If it's odd, you do not. So we get y equals the cube root of x plus 1 over 2. Technically, this is really poor notation to leave a fraction in a radical, but we're just going to let it go today. I know, it's crazy. So, final step, instead of y, we need to write f inverse of x. Questions there? We're going to do one more, but I want to change the next problem. I want to give us another fraction. I think we need that more. So we are going to do, let's find the inverse of f of x equals x minus 3 over x plus 4. Do you guys want to try it on your own first?
Yeah.
Okay, so try to find the inverse. If you get done, do domain and range for the function and the inverse. Switch x and y, and we now have 2 y's in the problem. Get rid of the fraction, so you multiply over the y plus 4. Then what'd you do? Okay, so if you subtract over y and your 4x, factor out your y. When you do that, what's y divided by y? 1, so make sure you have the 1 there. Then you can divide. Final step, you have f inverse. Now, yours could look a little different. So just depending on which side you moved everything to, you could have this or 4x plus 3 over 1 minus x. Those are equivalent, so either answer is okay. Negative 4x minus 3, sure. All right. Domain of the original function. So looking back at the original, my denominator was x plus 4, so what can't I have? Negative 4. So it would be negative infinity to negative 4 union negative 4 to infinity. And I know automatically that is the same as the range of the inverse. Looking at the inverse, what can x not be? 1. So the domain of the inverse would be negative infinity to 1, union 1 to infinity, and that's the same as the range of the original function. We do still have a few minutes before lunch. The homework assignment is on here. We will do a work day on Tuesday, so this is due on Wednesday.